Finally, the wait is almost over. Something unexpected just happened. Right now, this very moment, there are images sitting on NASA's servers that could change everything we understand about visitors from beyond our solar system, and the only thing stopping you from seeing them is a government shutdown. On October 31st, 2025, something unprecedented happened. A member of Congress sent a letter to NASA that forced the agency into a corner, demanding they acknowledge what they'd been quietly holding back. High-resolution images of 3I Atlas captured by instruments most people don't even know were watching. And here's the twist. NASA didn't deny it. They didn't deflect. They made a promise, a specific time-bound commitment that those images would be released as soon as government reopens. Think about what that means. The data exists. Scientists have likely already seen it. Preliminary analysis may already be sitting in internal reports. But you, the public whose tax dollars funded these observations, you're locked out. Not because of some shadowy conspiracy, but because of timing, bureaucracy, and a government shutdown that nobody saw coming. Now, before you dismiss this as another conspiracy rabbit hole, let me be absolutely clear about what actually happened here. This isn't speculation. This is congressional record. Congresswoman Anna Paulina Luna, a Republican representative from Florida's 13th District, former Air Force veteran, member of the House Committee on Oversight and Accountability. She didn't send a casual inquiry. She sent a formal letter directly to NASA's acting administrator on Halloween, October 31st, 2025. The letter was specific. It named 3I Atlas. It requested acknowledgement of observations made by Mars-based instruments during the comet's closest approach in early October. And critically, it asked NASA to commit to a public timeline for releasing that data. Luna wasn't asking NASA to investigate something hidden in classified archives. She was asking them to acknowledge what they already possessed and tell the American people when they'd get to see it. And NASA responded. That's the part that makes this story different from typical government secrecy narratives. NASA didn't bury the request in bureaucratic runaround. They didn't claim the data didn't exist. They didn't cite national security concerns or proprietary scientific protocols. They said yes, they committed. Images and observational data would be released once government operations resume normal function. This creates a fascinating dynamic. As you're watching this right now, those images physically exist in digital storage at NASA facilities. They're not being processed anymore. Processing is likely complete. They're not awaiting scientific review. Internal teams have almost certainly examined them. They're simply waiting for the administrative machinery of government to restart so the public release valve can open. You might be thinking, okay, but isn't data release just standard procedure? Why does this matter? And you're absolutely right to ask. NASA releases astronomical data all the time. Hubble images appear in public databases within weeks of capture. James Webb, Space Telescope observations get published and celebrated. Ground observatories share findings freely. The scientific community operates on principles of transparency and peer review. Data flows. That's how it's supposed to work. But 3I Atlas isn't a normal observation target. It's the third confirmed interstellar object in human history. Only the third visitor from beyond our solar system that we've definitively detected and tracked. And the observations Luna specifically requested in her letter weren't from the usual suspects like Hubble or JWST, instruments that already have publicly available 3I Atlas imagery. Luna's letter targeted something different, something more specific. According to sources familiar with the Congressional inquiry, Luna asked for data from NASA's Mars reconnaissance orbiter, particularly the HiRISE camera system. Now, if you're not familiar with HiRISE, let me give you context. HiRISE stands for High Resolution Imaging Science Experiment. It's a camera mounted on the Mars reconnaissance orbiter that was designed primarily for mapping the Martian surface in extraordinary detail. This instrument can detect features as small as a meter across from Mars orbit. It's the reason we have those stunning, almost unbelievable close-up images of Mars's surface. The ones where you can see individual boulders, crater textures, and geological formations with clarity that feels like you're standing on the planet yourself. But HiRISE isn't limited to pointing down at Mars. It can be oriented towards space. And when 3I Atlas passed within approximately 30 million kilometers of Mars in early October 2025, multiple spacecraft were positioned to observe it, including Mars Reconnaissance Orbiter, including HiRISE. Now here's where the timeline becomes absolutely crucial, because timing reveals intent. Let me walk you through this step by step. October 2nd through 3rd, 2025, 3i Atlas reaches its closest approach to Mars. 30 million kilometers might sound distant, but in astronomical terms that's practically a neighbor stopping by for coffee. Both NASA's Mars Reconnaissance Orbiter and ESA's Mars Express and ExoMars missions had viewing opportunities. Instruments were positioned, observations were scheduled and executed, data was collected. Then, October 29th through 30th, 2025, 3i Atlas reaches perihelion, its closest approach to the Sun. This is when any comet becomes most active, most bright, most observable. The object is at peak visibility. Space telescopes, ground-based observatories, every available platform that can capture data is focused on this moment. Observations flood in from around the world and from instruments in orbit. Then, October 31st, 2025, Luna's letter arrives at NASA. She requests acknowledgement and commitment to release specifically Mars-based observation data. She also suggests NASA prioritize observations using the Juno spacecraft, which is currently near Jupiter. The letter creates a congressional record. It's formal, it's specific, it's public. November 1st and 2nd, 2025, the United States government enters shutdown. Non-essential federal operations pause. NASA's essential operations continue because you can't just turn off spacecraft or stop monitoring satellites. But public communication systems, administrative processing, routine data release activities, all of that freezes. Standard processing that might have been days away from completion halts. Data that was queued for publication gets stuck in the pipeline. The administrative staff required for formal data releases aren't working. The machinery of government transparency literally stops functioning. November 3rd through 5th, news breaks about Luna's inquiry. Media outlets start reporting. Social media lights up. The story develops legs. Congress demands NASA release 3i Atlas images. Public attention increases. Scientific community starts asking questions. The conversation goes from insider circles to mainstream awareness. Then, November 6th, 2025. According to reports, NASA has a meeting or conversation with Congresswoman Luna. Details aren't heavily publicized, but NASA reiterates its commitment. Data will be released as soon as government reopens. The promise stands. The timeline is confirmed. And now we wait. Think about what this sequence reveals. NASA had the data before Luna's letter. Data processing was already underway. Luna formalized congressional pressure to commit to public release. NASA agreed to a specific condition: government reopening. Then government shut down, creating the delay we're experiencing now. The promise remains valid. The commitment is on record. But the timeline is dependent on an external factor that NASA doesn't control: congressional action to end the shutdown and resume normal government operations. This isn't a story about NASA hiding something sinister. This is a story about institutional accountability, congressional oversight functioning as designed, and the messy reality of how government transparency actually works when timing and bureaucracy collide. Now, here's what makes Luna's involvement particularly interesting. She didn't randomly decide to write this letter. Congressional representatives don't typically send formal letters to NASA about specific astronomical observations unless there's a reason. Luna's background includes strong interest in government transparency and space-related oversight. She's been involved in investigations of government space programs before. She understands how to use congressional authority to enforce accountability. But the letter itself reveals something else. Luna specifically mentioned the scientific importance of 3i Atlas observations. She emphasized the need for advanced observations and suggested funding additional observations with Juno. This language suggests Luna or her staff had reviewed available information about 3i Atlas and determined the scientific value justified congressional attention. She wasn't pushing conspiracy theories. She was advocating for scientific data access. There's a massive difference between those two approaches, and the language of Luna's letter clearly falls on the transparency side, not the conspiracy side. So here's the real question viewers are asking. Why would Congress get involved in what should be routine data release? Multiple possible answers exist, and they're not mutually exclusive. First possibility, Luna's office received inquiries from researchers or scientists who believed important observational data was being unnecessarily delayed and wanted congressional intervention to speed the process. Second possibility, Luna's own interest in space transparency led her to notice the gap between observations happening in early October and data not appearing in public databases by late October, prompting her to investigate why. Third possibility, preliminary reports or analyses from researchers like Avi Loeb, who's been vocal about 3I Atlas's unusual characteristics, suggested the data had scientific significance worth ensuring public access. Any or all of these factors could have motivated Luna's letter. What matters is the result: formal congressional pressure, institutional acknowledgement, and commitment to timeline. The system worked, oversight functioned, accountability was enforced, the data will be released. That's what this story is actually about. Not hidden conspiracies, but transparency mechanisms functioning, even if slowly and imperfectly. But here's what you need to understand as we go deeper into this analysis. Luna's letter forced NASA to be transparent about timeline. NASA couldn't respond with vague promises or indefinite delays. The congressional record creates accountability. When NASA said as soon as government reopens, that becomes a measurable commitment. If government reopens and data doesn't flow within reasonable timeframe, Luna has grounds to follow up with additional oversight. This creates institutional pressure that wouldn't exist without congressional involvement, and that pressure matters because it sets precedent. It signals to NASA and other agencies that congressional oversight of publicly funded research data release is real and will be enforced. This affects future decisions about whether to delay releasing data, how long delays are acceptable, and what justifications are legitimate. Beyond 3I Atlas, beyond this specific case, Luna's letter reinforces the principle that taxpayer-funded observations should be taxpayer-accessible in timely fashion. That principle is worth defending, which is exactly what Luna's letter accomplished. So if you're intrigued by this story, if you want to understand not just what's happening with 3I Atlas, but why institutional transparency matters for science and public knowledge, then I need you to do something right now. Hit that like button so this video reaches more people who care about government accountability and scientific access. Drop a comment telling me where you're watching from and what your biggest question is about these unreleased images, because the engagement from this community directly affects how much attention this story gets when the data actually drops. And when government reopens and NASA fulfills its promise, we're going to analyze those images together. We're going to examine what scientists discover. We're going to hold NASA accountable to its commitment. But that only happens if this community stays engaged and demands that transparency. So let me know you're here. Let me know you're paying attention. Now, let's talk about what we're actually waiting to see. Before you can understand why Luna's letter was necessary, before you can grasp why congressional intervention mattered, you need to understand what observational data actually exists about 3I Atlas, and which pieces the public has already seen versus which pieces remain locked away. Because this isn't about all data being hidden. Some observations have been released openly and analysed publicly, others haven't. And that gap, that specific difference between what's public and what's not, that's where the story lives. Let me start with what's already confirmed and publicly available, because transparency matters and I'm not going to pretend everything is secret when it's not. Between August 7th and 15th, 2025, NASA's SphereX Observatory and the James Webb Space Telescope conducted observations of 3I Atlas. The data revealed composition, significant amounts of carbon dioxide, water, carbon monoxide, and various organic molecules. These findings were published relatively quickly after data collection. You can find JWST images in NASA's public archive right now, this moment, if you go looking. Scientists presented composition findings at conferences. Press releases went out. Science communicators explained the significance. This data flowed freely into both the scientific community and public awareness. Nobody hid it. Nobody delayed it unnecessarily. The system functioned exactly as it should. Hubble Space Telescope imaged 3I Atlas on July 21, 2025, and during subsequent observations capturing details of the comet's dust envelope structure and coma. Again, public images available. NASA databases have these observations catalogued and accessible. Researchers downloaded them, analysed them, published papers examining the findings. The European Space Agency's Mars Express and ExoMars Trace gas orbiter obtained observations during Mars' closest approach on October 3, 2025, when the comet was approximately 30 million kilometers from Mars. ESA coordinated these observations publicly. They released findings through official channels. They engage with the scientific community openly. So far, everything I've described represents normal science functioning normally. Data collected, processed, released, analysed, and communicated to public. No delays, no mysteries, no problems. But then we get to Mars Reconnaissance Orbiter and its HiRISE camera system. And here the timeline becomes noticeably different. HiRISE was specifically designed for high-resolution imaging. It's an extraordinary instrument, capable of resolving features on Mars's surface down to 1 meter across. When you see those stunning images of Mars that look almost like aerial photography from Earth, where you can identify individual rocks and see the texture of sand dunes, that's HiRISE. The camera can be oriented toward targets beyond Mars. And when 3i Atlas passed Mars in early October, multiple sources, including researchers like Harvard astrophysicist Avi Loeb, have claimed that HiRISE captured observations of the object. Loeb has specifically suggested these images provide detail not available from other instruments. Now here's the transparency moment I promised you. As of now, NASA has not officially confirmed HiRISE data from 3i Atlas observations in its public databases. This is verifiable fact. If you search NASA's HiRISE public archive, you won't readily find 3i Atlas imagery catalogued the way typical Mars surface observations are. The data either hasn't been released yet or hasn't been processed for public access. Either way, it's not in your hands. It's not available for independent scientific examination, and that absence creates questions. Multiple possible explanations exist for this delay, and I need to be transparent about each one because jumping to conclusions serves nobody. Reason 1. Technical processing delays. HiRISE data requires substantial processing. Raw sensor data doesn't automatically become beautiful images. It must be calibrated for sensor characteristics, corrected for orbital motion and position, validated against reference points, formatted for scientific distribution, and reviewed for quality. For a moving target like a comet, this processing is significantly more complex than imaging a stationary Martian surface feature. You're not comparing to a reference map. You're capturing a dynamic object moving through space. The algorithms are different. The processing time extends. Weeks or even months of delay could be genuinely legitimate technical necessity, not intentional withholding. Reason 2. Mission constraints. Mars reconnaissance. Orbiter is a resource-intensive mission, pointing the spacecraft, collecting data, transmitting it to Earth, processing results. All of this requires allocation of mission operations time, personnel, and computational resources. During government shutdown, essential operations continued, but non-essential data processing could legitimately deprioritize. If 3i Atlas observation processing was scheduled but not yet complete when shutdown hit, it would get stuck in queue. That's not conspiracy. That's mundane bureaucratic reality. Reason 3. Scientific verification protocols. NASA has institutional procedures for releasing data, especially data that might be interpreted as surprising or controversial. If HiRISE images showed unexpected features, unusual nuclear structure, atypical tail morphology, composition variations, anything that didn't fit standard comet models, NASA might engage internal peer review or verification before public release. This isn't hiding information. It's institutional caution about releasing data that will inevitably be interpreted, misinterpreted, analysed, and debated publicly. NASA wants scientific context before that circus begins, particularly given existing speculation about 3i Atlas's characteristics. That's legitimate institutional behaviour. Reason 4. Government shutdown pause. The most obvious factor. When government shut down November 1st and 2nd, administrative functions froze. Data release protocols depend on administrative staff, documentation procedures, public communication systems, all of which paused. Essential spacecraft operations continued because you can't turn off satellites, but routine data publication, database updates, public communications, all of that stopped. If HiRISE data was days away from release when shutdown hit, it got stuck. Not because anyone decided to hide it, but because the machinery of government literally stopped turning. Now, here's what matters. None of these reasons are illegitimate. Processing complex data genuinely takes time. Institutional caution before public release is appropriate given how findings will be received. Shutdown delays are real external constraints NASA doesn't control, but collectively, these factors created a situation where Mars-based observations existed but weren't publicly accessible, while space telescope data had already been released weeks or months earlier. From an outside perspective, this looks like selective release. It looks like some data flows freely while other data gets bottlenecked, and perception matters because it affects public trust in institutions. Even if the explanations are completely legitimate, the appearance of delay creates suspicion. That's the gap Luna's letter addressed. By formalizing congressional inquiry, she essentially said, acknowledge this data exists, commit to a timeline for release, and end the perception that information is being managed or controlled. NASA's response, commitment to release once government reopens, directly addressed that perception gap. The promise created accountability. The timeline became measurable. The institutional record now includes that commitment. But I need to be crystal clear about something because credibility matters more than clicks. I've used language like HiRISE images and Mars observations, but there's a difference between what's confirmed and what's being claimed. Here's what's confirmed. Mars-based spacecraft were positioned to observe 3I Atlas during closest approach. That's documented in mission planning records from both NASA and ESA. Mars Reconnaissance Orbiter has HiRISE camera capability. That's technical specification, not speculation. Luna's letter specifically requested Mars observation data. That's congressional record, publicly available. NASA committed to releasing data once government reopens. That's official NASA statement in response to Luna's inquiry. Those facts are solid. But here's what's claimed but not officially confirmed. Whether HiRISE specifically captured usable imagery of 3I Atlas. Researchers like Avi Loeb have suggested this, but NASA hasn't officially confirmed the status or quality of such observations. What specific resolution or detail such imagery would contain? That's speculative until data releases. Whether such imagery reveals unusual features beyond what other telescopes have shown, that's circulating among researchers but not officially stated by NASA. And what remains completely unknown, the exact processing timeline for Mars orbital data, whether current delays relate solely to technical processing or involve other factors, and what findings will actually be in official releases when they happen. I'm stating this clearly because I'm not interested in building hype on speculation. The fact that Luna's letter exists is real. The fact that NASA made a commitment is real. The fact that data hasn't been released yet is real. But the specifics of what's in unreleased imagery and why exactly delays happened beyond the general categories I mentioned, those involve inference, interpretation, and connecting dots that might not connect the way we think. What we know for certain from both ESA and NASA documentation is that Mars-based observations of 3I Atlas during October closest approach occurred. ESA has released preliminary findings from its instruments. NASA's data processing would include similar observations from its instruments. The difference is timing and public access. ESA moved faster, NASA's process took longer. Why the discrepancy? Could be mission priorities, could be processing complexity, could be institutional procedures, could be shutdown timing. We don't definitively know. What we do know is that Luna's letter forced acknowledgement and timeline commitment, which is exactly what congressional oversight should accomplish. One more timeline detail matters here. ESA's JUICE mission, a spacecraft currently travelling toward Jupiter, will attempt additional observations of 3I Atlas in November 2025, with data expected by February 2026. That extended timeline reveals something important. Comprehensive analysis of 3I Atlas observations involves more processing, more coordination, and more time than initial expectations suggested. This isn't just about downloading data and publishing images. This is about multiple instruments, multiple spacecraft, multiple agencies coordinating observations and analysis. The scope is genuinely complex. So when NASA says data will be released after government reopens, that doesn't mean instant publication. It means the administrative machinery restarts, processing continues, and publication happens when proper procedures complete. Could be days after reopening, could be weeks. The commitment is to release, not to instant gratification. So the real story isn't that NASA is hiding spectacular secret discoveries in a vault somewhere. The real story is that standard data processing timelines, government shutdown interruption, and institutional verification protocols combine to create a gap between observation and public availability. Luna's letter addressed that gap directly. NASA responded with commitment and transparency. Now we wait for government to reopen so the administrative machinery can complete its function. That's not exciting conspiracy drama. That's how institutions actually operate. But here's what makes it genuinely interesting. Different instruments see different things. JWST sees composition, what molecules are present. Hubble sees structure, the shape and morphology of dust and gas. HiRISE sees high-resolution detail, the specific features, textures, and characteristics that lower-resolution instruments miss. When all these datasets combine, astronomers can build complete pictures. Maybe that complete picture shows exactly what comet models predict. Maybe it reveals something that challenges existing models. Maybe it shows features that require revised understanding. We genuinely don't know until data releases and comprehensive analysis happens. That's the real suspense. Not conspiracy, not hidden aliens, but genuine scientific uncertainty about what complete information will reveal about an object from beyond our solar system. And that uncertainty is worth maintaining attention for, because whatever the data shows, we'll be smarter about the universe once we've seen it and analysed it properly. So stay with me, because understanding what happens next requires understanding the timeline and when this data will actually become accessible. Let me map out exactly what happened and when, because in institutional analysis, timelines reveal intent, priorities, and the real mechanisms of how government transparency actually functions. October 1st through 3rd, 2025, Mars' closest approach window opens. Multiple spacecraft positioned to observe 3I Atlas as it passes approximately 30 million kilometers from the red planet. NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, ExoMars Trace Gas Orbiter. All of these instruments have viewing opportunities. Data collection occurs, observations are captured, raw data begins flowing back to Earth through the deep space network. At this point, everything is proceeding normally, missions are executing planned observations, no delays, no issues, just science happening as scheduled. Then October 29th through 30th, 2025, perihelion, the moment when 3I Atlas reaches its closest approach to the Sun. This is the astronomical money moment. When any comet reaches perihelion, it's at maximum brightness, maximum activity, maximum observability. Solar radiation heats the nucleus, outgassing intensifies, the tail becomes most visible. Every available telescope that can capture data focuses on this opportunity. JWST, if it has observation windows, ground-based telescopes across the globe tracking the object, any remaining space assets with line of sight. Data floods in from multiple sources, observations accumulate, the scientific community is actively engaged and collecting information. October 31st, 2025. This is when everything changes. Congresswoman Anna Paulina Luna sends her formal letter to NASA's acting administrator. The letter is specific. It names 3I Atlas. It requests acknowledgement and commitment regarding observational data, particularly Mars-based observations. It suggests NASA prioritize additional observations using Juno spacecraft near Jupiter. This isn't casual inquiry. This is formal congressional correspondence creating official record. Luna is using institutional authority to enforce accountability. The letter forces NASA into response mode. They can't ignore congressional inquiry. They must acknowledge, address, and commit. And they do. NASA responds, according to reports and statements, committing to data release as soon as government reopens. That phrase is crucial. As soon as government reopens is specific condition. It's measurable, it's accountable, it creates timeline dependent on external factor, but timeline nonetheless. NASA didn't say, eventually, or when we're ready, or under review. They gave specific trigger, government reopening. That matters legally and institutionally. Then November 1st and 2nd, 2025, the United States government enters shutdown, and this is where external reality crashes into institutional commitments. Non-essential federal operations pause immediately. NASA's essential operations continue because spacecraft don't understand government shutdowns, and you can't just power down satellites or stop monitoring critical systems. But everything that isn't directly related to maintaining spacecraft operations or safety-critical research, that stops. Public communications offices close. Administrative staff who handle data release protocols aren't working. The personnel who update public databases, format releases, coordinate with press offices, manage documentation, all of that pauses. Standard processing that might have moved forward in normal circumstances hits a wall. Data that was queued for publication gets stuck in digital limbo. The administrative machinery that enables transparency literally stops functioning. November 3rd through 5th. News breaks. Media outlets start reporting on Luna's congressional inquiry. The story develops. Congress demands NASA release. 3i Atlas images. Social media lights up. Scientific community starts asking questions. Public attention increases. People who had never heard of 3i Atlas suddenly want to know what Congress is demanding and why NASA needed congressional pressure to commit to release. The narrative builds momentum. And this attention is actually valuable because it creates additional accountability pressure. NASA knows the public is watching now. Luna knows the public is watching. When government reopens, both parties will be accountable to public expectation that data actually flows. Then November 6, 2025, according to reports, NASA has meeting or conversation with Congresswoman Luna. Details aren't heavily publicized in media coverage, but the substance is clear. NASA reiterates commitment to release data once government reopens. This November 6th interaction represents formal governmental coordination. Luna wanted confirmation that commitment stood despite shutdown. NASA provided that confirmation. The promise remains valid, timeline remains conditional on government reopening, but commitment itself is solid. This creates official record that both parties acknowledge and accept. November 6th through present. Government shutdown continues. Expected duration uncertain because government shutdowns are inherently political processes that resolve based on congressional negotiation, not predetermined schedules. Historical patterns suggest shutdowns last anywhere from days to weeks, occasionally extending longer if political conditions prevent resolution. During this entire period, data remains in processing queue. It's not being actively hidden. It's not being deliberately suppressed. It's sitting in digital storage waiting for administrative machinery to restart so release protocols can execute. Scientists at NASA likely have internal access. Preliminary analysis might be occurring within the agency. But public release requires administrative function, documentation, database updates, communications coordination, all of which remain paused. Post-government reopening, whenever that occurs, this is when actual release happens. Once government operations resume normal function, administrative staff returns to work. Data processing resumes for non-essential but valuable scientific activities. Public release protocols reactivate. NASA publishes HiRISE data, Mars reconnaissance orbiter findings, coordinated Mars mission observations to public databases. The data becomes accessible. Scientists outside NASA can download it. Independent analysis begins immediately, and the scientific community starts comprehensive examination of what the observations actually show. Timeline estimate based on how NASA typically operates. Within days to 2 weeks of government reopening, expect data to appear in NASA's public databases and archives. Researchers will begin downloading and analyzing immediately. Preliminary scientific findings, informal communications among research groups, and early interpretations will start circulating within 2 to 4 weeks after release. Formal scientific papers with peer review will take months, but informal scientific community discussion will happen much faster. Now here's what's genuinely fascinating about this timeline. It's completely dependent on external factor NASA doesn't control. NASA can't release data while shutdown restricts operations. They physically could dump raw data onto servers, but that's not how proper data release works. It requires documentation, quality assurance, proper formatting, database integration, public communications, all administrative functions that require staff and systems currently offline. So NASA's promise of as soon as government reopens is both genuine and dependent on congressional action to end shutdown. This creates interesting institutional dynamic. Luna asked for data release. NASA said yes, but timing depends on government operations resuming. This actually puts pressure on Congress itself. If Luna and her colleagues want data released, they need to resolve shutdown. If they don't resolve shutdown, data remains stuck, and public perception shifts toward blaming congressional dysfunction rather than NASA delays. The accountability cuts both ways, which is exactly how institutional checks and balances should function. You might be wondering why NASA doesn't just release data during shutdown on its own initiative, bypassing normal procedures. The answer is procedural and legal. Government agencies operating under shutdown conditions have specific limitations on what activities they can undertake. Essential operations continue. Non-essential operations pause. Data release, while valuable and important, isn't typically classified as essential operation unless it involves safety-critical information or emergency response. So even though NASA wants to release the data, even though they've committed to release, they're bound by shutdown operational constraints. They can't bypass procedures without potentially violating government operation regulations during shutdown. This might feel frustrating if you're eager to see the data, but it's actually important that agencies follow proper procedures even when those procedures slow things down. Rules matter, process matters. Institutions that bypass procedures when convenient tend to bypass them in less benign circumstances too. So NASA following proper shutdown protocols even when it delays something we want is actually NASA functioning with institutional integrity. The commitment to release once government reopens shows they're prioritizing transparency within legitimate procedural constraints. One more temporal detail creates urgency. The comet itself is leaving. 3. HiAtlas continues its trajectory through the solar system, heading outbound toward interstellar space. The object will exit inner solar system observability between late November and late December 2025. After December, observations become increasingly difficult as distance increases and brightness decreases. This creates natural deadline. Data release should happen before the object becomes too distant for follow-up observations or additional analysis. The scientific window closes. If data isn't released and analysed before late December, opportunities for additional observations or verification studies disappear. The comet continues into the dark, and whatever questions the data raises might not be answerable without the object still in range. This creates genuine institutional incentive. NASA knows observations are time-sensitive. Luna's letter reinforces that timing matters. Everyone involved understands delaying past late December becomes scientifically problematic. This actually creates pressure for rapid data release once government reopens. NASA will likely prioritize getting this data public quickly, not just because of congressional commitment, but because scientific value diminishes with every passing week as the object moves farther away. So when you're wondering about timeline, factor in this urgency. Data release probably happens quickly after reopening specifically because delay costs scientific opportunity, and that brings us to the question everyone actually wants answered. What will the data show, and why does the scientific community care so much about these specific observations? To understand why Luna's congressional inquiry mattered, you need to understand why the scientific community is genuinely interested in these specific observations. And we need to be extraordinarily careful here about distinguishing verified observations from circulating speculation, because mixing those two categories destroys credibility and serves nobody. Let me start with what's actually confirmed about 3I Atlas beyond any doubt. 3I Atlas is the third confirmed interstellar object ever detected in human history. The first was Oumuamua in 2017, a strange elongated object that passed through our solar system and sparked intense scientific debate and public fascination. The second was 2I/Borisov in 2019, which appeared more conventionally comet-like and helped establish baseline expectations for interstellar visitors. Now we have 3I Atlas, discovered earlier in 2025 and tracked as it approached the inner solar system. Its trajectory is hyperbolic, meaning it's not gravitationally bound to our Sun. It came from somewhere else. It's passing through, and it will leave, continuing into interstellar space beyond our solar system. That basic fact makes any data about this object inherently valuable. We're studying a visitor from beyond our stellar neighborhood, an object that formed around a different star, potentially in radically different conditions than our solar system's formation environment. Every measurement, every observation, every data point expands human understanding of how planetary systems form and what diversity exists in the galaxy. Spectroscopic data from JWST and other instruments confirmed the object contained significant amounts of carbon dioxide, water vapor, carbon monoxide, and various organic molecules. The specific ratios and abundances don't perfectly match typical solar system comets, suggesting formation in different conditions or from different primordial materials. This is scientifically interesting because it provides evidence about chemical composition in other stellar systems. We're essentially sampling material from another star's planetary formation process. That's extraordinary data for understanding galactic chemical diversity and planetary system formation physics. The object has also demonstrated behaviors that caught scientific attention. Non-gravitational acceleration, the comet's trajectory deviates slightly from purely gravitational prediction. This isn't unusual for comets. Outgassing creates thrust that affects trajectory. But the magnitude and timing of these deviations were slightly unexpected based on initial models. Asymmetric tail structure appeared in some observations, with the dust tail showing irregularities that suggested non-uniform outgassing or unusual nucleus rotation. Color variations appeared across different wavelengths, indicating compositional differences across the surface or complex outgassing chemistry. Brightness changes exceeded some model predictions, suggesting more active outgassing than initial size estimates would predict. These observations are real. Multiple observatories documented them. They're not disputed. They're facts that require scientific explanation. Now here's where we enter speculative territory, and I'm going to be completely transparent about that distinction. When these anomalies were first observed and documented, some researchers, most notably Harvard astrophysicist Avi Loeb, suggested the combined observations warranted detailed investigation to determine whether standard cometary physics could explain everything or whether unusual properties might indicate something unexpected. Loeb wrote publicly that characteristics like non-gravitational acceleration, unusual tail structure, and brightness variations merit examination. He suggested, and this is where media often misrepresents his position, that the data should be examined thoroughly to understand what's actually happening. He did not claim the object was definitively artificial. He advocated for data transparency and rigorous investigation. Those are fundamentally different positions. A researcher saying this data is interesting and should be examined carefully is not the same as claiming this is definitely aliens. But that nuance gets lost in social media translation, where researcher suggests unusual properties warrant investigation becomes scientist claims object might be alien spacecraft. The transformation happens through game of telephone, and by the time it reaches general public consciousness, the message has morphed into something the original researcher never actually said. Other mainstream researchers have proposed that anomalies could indicate unusual composition, perhaps nickel-rich materials, or unexpected ice compositions that would affect outgassing patterns, or unexpected outgassing sources distributed asymmetrically across the nucleus, or rotation characteristics that create unusual light curve patterns. These are legitimate scientific hypotheses, their proposals worth examining, but they're hypotheses, not confirmed facts. The scientific method involves exactly this process: observing unexpected patterns, proposing explanations, testing those explanations against data, accepting or rejecting based on evidence. Most scientific hypotheses get rejected. That's normal. That's how science works. The ones that survive repeated testing become accepted theory. The ones that don't get discarded and replaced. So when researchers propose explanations for 3I Atlas's unusual properties, they're doing science correctly. They're not making definitive claims. They're suggesting possibilities that data might test. Why do Mars observations specifically matter in this context? High-resolution imaging from Mars orbit provides information other telescopes struggle to achieve. If HiRISE captured detailed images of 3I Atlas's nucleus or inner coma, those images could show precise dimensions of the nucleus, essential for calculating mass, density, and compositional estimates. Surface texture and structure, if visible at sufficient resolution, could indicate whether the object is monolithic or fragmented, smooth or rough, homogeneous or heterogeneous. Jet source locations, the specific places where material is outgassing from the nucleus, would be visible if resolution is sufficient, allowing scientists to map activity patterns. Tail morphology and dynamics at high resolution could reveal dust grain sizes, distribution patterns, and ejection velocities that inform outgassing physics models. Composition variations across the surface, if spectroscopic data accompanies imaging, would show whether the object is chemically uniform or heterogeneous. This level of detail, combined with data from space telescopes and ground observatories, would let researchers build complete three-dimensional models of the object. Not just, here's what it looks like from one angle, but here's its actual physical structure, composition, behavior patterns, and characteristics. The scientific question isn't whether these images prove aliens. The scientific question is whether complete data lets us explain observed anomalies through conventional cometary physics, or whether anomalies persist even after accounting for composition and structure. If complete datasets show all observed behaviors fit cometary models once you account for unusual but plausible composition, maybe higher metal content than typical, maybe unexpected ice distribution, then scientific conclusion is, interesting comet, expanded our understanding, valuable data, move forward with refined models. If complete datasets show some behaviors genuinely don't fit models even after accounting for plausible compositional variations, then scientific question becomes, what are we missing in our understanding of cometary physics? This could lead to revised theoretical models, new physics proposals, additional observations of other objects to test new hypotheses. Either outcome is scientifically valuable. We learn either way. We're not searching for one predetermined answer. We're searching for whatever answer the data actually supports. The Avi-Loeb factor deserves clear explanation because his name appears repeatedly in 3I Atlas discussions. Loeb has history of proposing unconventional explanations for astronomical observations. His work on Oumuamua, where he suggested the object might be artificial based on its unusual acceleration and elongated shape, generated substantial controversy. The mainstream scientific community examined his hypothesis carefully and concluded the evidence didn't support artificial origin. Natural explanations, while requiring some unusual assumptions about composition, adequately explained observations. Loeb's hypothesis was tested and found insufficient. That's how science should work. The fact that Loeb proposes unconventional explanations isn't inherently wrong. Science needs people willing to challenge conventional thinking. But it also doesn't mean his proposals are correct just because he suggests them. Most revolutionary scientific ideas are wrong. The few that survive testing become breakthroughs. The many that don't become footnotes. Loeb's interest in 3I Atlas isn't conspiracy. It's consistent with his research approach of examining data that challenges conventional understanding and proposing alternative hypotheses for testing. If data supports his interpretations, scientific community will acknowledge that. If data supports conventional explanations, he'll likely acknowledge that or refine his hypothesis. This is normal scientific process. Why did Luna care enough to demand data release? This is actually the most interesting institutional question. Congressional representatives don't typically intervene in specific astronomical data releases unless constituents, researchers, or political factors create motivation. Possible explanations. Luna received requests or pressure from researchers or scientific organizations who believed data was being unnecessarily delayed. She identified data access as transparency issue consistent with her oversight interests. She was briefed on scientific significance and wanted to ensure publicly funded research reached public domain in timely fashion. She recognized this as opportunity to demonstrate congressional oversight effectiveness. Any or all of these factors could have motivated her letter. What matters isn't her personal motivation. What matters is the result. Formal congressional pressure enforcing institutional accountability for data release. The principle being enforced is that publicly funded observations should be publicly accessible in reasonable timeframes. That principle transcends any individual case and sets precedent for how government scientific agencies handle data transparency. What does data release actually enable for science? When NASA releases complete datasets, here's what immediately becomes possible. Peer review. Scientists outside NASA examine raw data and NASA's analysis, verifying or questioning findings. Independent confirmation. Multiple research groups apply different analytical techniques to same data, seeing if conclusions hold across different approaches. Alternative analysis. Researchers with different expertise or theoretical frameworks might identify patterns NASA's teams missed. International collaboration. Scientists globally contribute specialized knowledge to comprehensive understanding. Public scientific communication, science communicators can explain findings to general audiences, raising scientific literacy. The value isn't NASA revealing one secret finding. The value is transparency enabling distributed scientific examination by global community of experts. Science works better when more qualified people examine the same data from different perspectives. That's why data release matters institutionally and scientifically. And that's why Luna's letter, regardless of her specific motivation, serves scientific progress by enforcing that release happens according to committed timeline. So the real question isn't whether we'll discover aliens in these images. The real question is what will comprehensive data analysis reveal about how objects from other star systems behave, what that teaches us about planetary system formation across the galaxy, and whether our current physics models adequately explain everything we observe or need refinement based on new information. Those are the questions worth getting excited about, and those questions can only be answered once data actually releases and the scientific community examines it thoroughly. Which brings us to what happens next and when you'll actually get to see what's in those images. Once government reopens and NASA publishes the complete 3i Atlas dataset including Mars-based observations, several things happen immediately, and the scientific process accelerates in ways that might surprise you if you're not familiar with how astronomical research actually functions. Within hours of data becoming publicly available, research groups worldwide download everything. Harvard, Princeton, MIT, Caltech, international universities across Europe and Asia, ESA research centers, independent astronomical organizations, hundreds of qualified scientists will immediately begin examining the data. This isn't NASA interpreting findings and everyone else passively accepting those interpretations. This is distributed scientific examination where multiple independent teams apply different analytical techniques, different theoretical frameworks, different areas of expertise to the same observational data. Some teams will focus on composition analysis using spectroscopic data. Others will focus on structural analysis using imaging data. Some will build trajectory models incorporating non-gravitational effects. Others will focus on outgassing physics and tail dynamics. Each team brings unique perspective and specialized knowledge. This distributed approach is crucial because it means no single interpretation dominates discussion. If data clearly shows anomalies, multiple teams propose competing explanations, and evidence determines which survive scrutiny. If data is unremarkable and fits standard models, multiple teams reach same conclusion independently, building confidence in findings. This is how scientific consensus actually builds, not through authority declaring truth, but through independent examination reaching convergent conclusions. The timeline of scientific response follows predictable pattern, based on how astronomical research typically proceeds. Immediate first 48 hours, preliminary analysis begins. Research groups download data, examine raw observations, conduct basic measurements and initial comparisons with existing data from other instruments. Social media and scientific communication platforms light up with initial impressions. Press releases from institutions whose researchers are involved. The scientific community starts informal discussion about what observations show. First week after release, detailed analysis intensifies. Teams compare Mars observation data with JWST, Hubble, and ground telescope observations looking for consistency or discrepancy. They examine whether new data supports previous interpretations or contradicts them. If anomalies exist in Mars data, researchers begin proposing explanations grounded in physics. If unexpected features are visible, speculation begins about implications for understanding the object's nature and origin. 2 to 4 weeks, first scientific papers get submitted. Research groups prepare preliminary findings for peer review, submitting to journals like Nature, Science, Astrophysical Journal, or specialized publications. These papers undergo editorial review and peer review process, where other experts examine methodology, challenge conclusions, identify weaknesses, and require revisions. Some findings get confirmed through this process. Others get questioned or require substantial revision based on reviewer feedback. This is science's quality control mechanism functioning. 2 to 3 months. First peer-reviewed papers get published. Early findings that survived peer review appear in journals. These papers receive citation by other researchers, get discussed in scientific community forums, and if findings are significant, broader media picks up on published research and communicates to general public. If findings are routine and confirmatory, scientific community notes results and moves forward with refined understanding, but without major paradigm shifts. 6 to 12 months. Comprehensive analysis papers appear. These represent detailed examination of complete datasets, where researchers have had time to fully process observations, cross-reference everything, conduct thorough modeling, and reach more confident conclusions. This is when scientific consensus really solidifies. Early interpretations either get reinforced by comprehensive analysis or get revised if additional examination reveals complexity initial analysis missed. By this point, the scientific community has reached working consensus about what the data actually shows and what implications exist for understanding interstellar objects. What could the data actually show when it releases? Let me give you 3 realistic scenarios without overstating or sensationalizing. Scenario 1. Data confirms conventional understanding. HiRISE images show standard comet nuclear structure consistent with known cometary bodies. Observed anomalies like non-gravitational acceleration and unusual tail structure get explained by compositional factors visible in the data, perhaps higher than expected metal content or unusual ice distribution that affects outgassing patterns. 3. iAtlas fits expanded but still conventional comet models. Scientific contribution is real. We've learned about diversity in interstellar comet populations, expanded our models to accommodate wider range of properties, and gathered valuable data about another stellar system's formation environment. Media result would be modest coverage, public interest passes relatively quickly, and research continues without major paradigm shifts. This is actually the most likely scenario based on how most astronomical observations turn out. Scenario 2. Data shows unexpected but explicable findings. Images reveal unusual nuclear structure, perhaps fragmented or asymmetric in ways that weren't predicted. Spectroscopy shows compositional ratios that don't fit standard models easily, but could be explained with revised formation theories. Outgassing patterns show unexpected sources or intensities that require refined physics models. Scientific contribution becomes more substantial. Researchers need to revise existing models of how interstellar comets form and behave, potentially leading to new theoretical frameworks about planetary formation in diverse stellar environments. Media result would be stronger coverage, science communicators explaining significance, sustained public interest, and potentially increased funding for follow-up observations of future interstellar objects. This scenario is possible and would be genuinely scientifically valuable. Scenario 3. Data shows findings that challenge models in fundamental ways. Observations don't fit predictions even after accounting for plausible compositional variations. Structure or behavior raises questions that known physics struggles to answer without invoking entirely new mechanisms. Multiple independent research teams examine the data and confirm unexpected findings, ruling out measurement errors or analytical mistakes. Scientific contribution would be major. Existing models require substantial revision. New physics might need to be proposed and tested. The entire framework for understanding comets and interstellar objects could shift. Media result would be extensive coverage, significant public interest that sustains for months, potential increase in research funding, and scientific community mobilization to explain what's happening. This scenario is least likely but not impossible. Science occasionally encounters observations that genuinely challenge existing understanding. When that happens, it's exciting, but also requires extraordinary caution to avoid overinterpreting limited data. All 3 scenarios represent legitimate scientific outcomes. None requires aliens or technology to be scientifically significant. Even scenario 1, where data simply confirms models, is valuable because confirmation is how science builds confidence in theories. Scenario 2 advances understanding meaningfully. Scenario 3 would be revolutionary, but would require extraordinary evidence to justify extraordinary conclusions. The scientific community will examine whatever the data shows with appropriate skepticism and rigor, reaching conclusions based on evidence rather than preference. What actually changes once data releases isn't predetermined. It depends on what data shows. But what definitely changes is transparency. Data moves from restricted institutional access to public scientific access. Accountability. NASA demonstrates congressional oversight effectiveness. Understanding, whatever the findings, we know more about this object than we did before. Research direction, depending on findings, future priorities might shift regarding how we observe and analyze interstellar objects. Public engagement, science communication brings findings to broader audience, potentially increasing scientific literacy and interest in astronomy. Those outcomes are guaranteed regardless of specific findings. The institutions have worked, accountability has functioned, and scientific understanding advances. That's worth recognizing as success, even if the data doesn't reveal anything sensational. Now, let me address directly the question that might be burning in your mind. Could this object actually be artificial? And what would evidence for that look like? Let's address directly the question everyone's thinking, but maybe hesitates to ask out loud. Could 3i Atlas be artificial? Could it be technological in origin? Here's my honest answer, and I'm going to give this to you straight without sensationalism or dismissive skepticism. We don't know yet. And that statement, we don't know, is actually how science is supposed to work. But I need to be extraordinarily clear about what we don't know actually means in this context, because there's an enormous difference between insufficient data to reach definitive conclusion and probably aliens but establishment won't admit it. Those are not the same thing at all. Let me lay out the spectrum of possibilities with intellectual honesty. On one end, you have the most probable explanation based on current evidence. 3I Atlas is a thoroughly conventional interstellar comet with some unusual but ultimately explicable properties that expand our understanding of how comets form in different stellar environments. The observed anomalies fit within known physics, once you account for compositional variations or structural characteristics we haven't fully characterized yet. This is the most likely scenario. Most astronomical observations that initially seem anomalous turn out to have conventional explanations once complete data becomes available and proper analysis is conducted. In the middle of the spectrum, you have a more interesting but still entirely natural explanation. 3. Atlas has properties that don't fit current comet models perfectly and requires us to revise our understanding of cometary physics, potentially indicating formation mechanisms or compositional ranges we hadn't previously considered. This would be scientifically significant, potentially leading to new theoretical frameworks, but still reflects natural processes rather than artificial construction. This outcome would be valuable and exciting for advancing scientific knowledge without requiring exotic explanations. On the far end of the spectrum, and I want to emphasize this is the least likely based on available evidence, you have the possibility that 3I Atlas exhibits properties that cannot be explained by any known natural process, even after exhaustive examination, suggesting technological origin or physical principles we don't currently understand. This is extremely unlikely, but not mathematically impossible. The universe is large and old. The existence of technological civilizations elsewhere is plausible given the scale of the cosmos. But plausibility doesn't equal probability for any specific object we observe. What would actually constitute evidence suggesting artificial origin? This is important because claims require appropriate evidence, and the more extraordinary the claim, the more robust the evidence needs to be. First requirement, structural anomalies that fundamentally violate known natural processes. We'd need observations of features that can't be explained by geology, chemistry, or physics as we understand them. Not just, this is unusual, but this violates conservation laws, or this exhibits geometry that natural formation can't produce. Second requirement, compositional markers strongly indicating intentional manufacture. We'd need material combinations, element ratios, or isotopic signatures that natural stellar or planetary processes can't create. Not just unusual composition, but composition that requires directed assembly or processing. Third requirement, behavioral patterns suggesting intelligence or responsiveness. We'd need trajectory changes that contradict gravitational mechanics and outgassing physics, or responses to environmental conditions that suggest deliberate action rather than passive physical response. Fourth requirement, independent confirmation by multiple research teams using different instruments and methodologies, with findings surviving peer review and attempted falsification. One team claiming something extraordinary isn't enough. The entire scientific community needs to examine the evidence and reach consensus that conventional explanations fail. Fifth requirement, exhaustion of natural explanations. Before entertaining artificial hypotheses, scientists would need to systematically attempt every plausible natural explanation and demonstrate why each fails to account for observations. Right now, none of these threshold conditions have been met for 3I Atlas. We have anomalies, yes. We have unexpected properties, yes. We have gaps in understanding, yes. But we don't have observations that require artificial explanation or that rule out all natural explanations. The anomalies observed so far, non-gravitational acceleration, unusual tail structure, brightness variations, these all have at least plausible natural explanations involving composition, structure, or outgassing behavior that we haven't fully characterized. They're interesting and worth investigating, but they're not evidence of technology. Let me address Avi Loeb's position accurately because media has often misrepresented what he's actually saying. Loeb has been portrayed as claiming 3I Atlas is definitely artificial or probably alien technology. That's oversimplification bordering on misrepresentation. What Loeb actually said is that observed anomalies warrant thorough investigation. He noted characteristics like non-gravitational acceleration and unusual properties merit examination to determine whether standard comet models adequately explain everything or whether data reveals something unexpected. He advocated for data transparency so the scientific community can conduct proper analysis. He suggested the possibility of unusual origin should be considered among hypotheses worth testing. None of that is claiming definitive artificial origin. That's advocating for rigorous scientific investigation without predetermined conclusions. Loeb's history with Oumuamua matters here. He previously proposed that Oumuamua might have artificial origin based on its unusual acceleration and shape. The scientific community examined that hypothesis carefully. Evidence didn't support it. The consensus conclusion was that Oumuamua was natural though unusual. Loeb's hypothesis was tested and found insufficient to explain observations better than natural explanations. That's exactly how science should work. Hypotheses get proposed, examined, tested, and either accepted or rejected based on evidence. Most hypotheses get rejected. That's normal scientific process. Loeb's willingness to propose unconventional explanations is valuable for keeping scientific discussion open and preventing groupthink. But his track record also shows his hypotheses often don't survive testing. That doesn't make him wrong for proposing them. It makes him a scientist doing what scientists should do, proposing testable ideas and accepting when evidence doesn't support them. His interest in 3i Atlas follows the same pattern. He's proposing investigation of unusual properties. He's not claiming definitive conclusions. That's legitimate scientific behavior. Why does speculation about artificial origin circulate so widely despite limited supporting evidence? Multiple psychological and sociological factors contribute. First, rarity generates interest. 3i Atlas is only the third confirmed interstellar object. Rarity makes things feel special and potentially significant beyond their actual characteristics. Second, genuine anomalies attract speculation. When scientists say this behavior is unexpected, public interpretation often becomes, this might be artificial, even though unexpected and artificial are completely different categories. Third, data gaps create uncertainty, and humans naturally fill uncertainty with speculation. When complete data isn't available, imagination fills the void. Fourth, media amplification transforms nuanced scientific statements into sensational headlines. Researcher suggests unusual properties warrant investigation becomes, scientist says mysterious object could be alien probe, through successive editorial transformations aimed at maximizing clicks. Fifth, community desire for the universe to be populated influences interpretation. Many people want to discover we're not alone. That desire affects how ambiguous information gets interpreted. None of these factors make artificial origin more likely. They just explain why speculation circulates. What will data release actually test? When NASA publishes complete datasets, the scientific community will examine whether observed anomalies fit natural comet models once you account for composition and structure revealed by high-resolution observations. If they do fit, even if models require some adjustment or expansion, then artificial hypothesis gets rejected and scientific understanding advances through refined natural explanations. If anomalies genuinely persist after accounting for all plausible natural factors, then researchers propose revised natural models before entertaining artificial alternatives. The process systematically eliminates conventional explanations before considering exotic ones. This is appropriate scientific methodology preventing premature jumping to conclusions that evidence doesn't support. Here's what I genuinely don't know and can't predict. What will the data actually show? I don't know if anomalies are fully explicable by composition and structure, or if they'll require revised physics models. I don't know if patterns will remain mysterious after complete analysis, or if they'll fit neatly into expanded understanding. I don't know if current theories will be confirmed or challenged. What I do know is that the scientific community will examine whatever the data shows with appropriate rigor, reach conclusions based on evidence through peer review and consensus building, and communicate findings transparently. The truth will emerge through that process, and we'll all understand the universe better afterward regardless of what specific conclusions emerge. My actual prediction, based on historical patterns of how astronomical anomalies typically resolve, is that data will show 3I Atlas is a genuinely interesting interstellar comet with properties that expand our understanding of cometary diversity and stellar system formation environments. It will likely have some characteristics requiring model adjustments or refinements. The scientific community will reach consensus about findings within months of comprehensive analysis. Public understanding will improve, and we'll move forward with more sophisticated knowledge about how interstellar objects behave. That outcome is exciting enough without requiring aliens. Detecting an object from another star system is extraordinary achievement. Understanding its properties advances human knowledge meaningfully. That's the story worth caring about. So here's my question for you right now. What do you genuinely hope the data shows, separate from what you think it will actually show? Hope and prediction are different. Hope tells us what we want to learn. Prediction reflects what evidence suggests. Both have value. Drop your answer in comments, and if this analysis has made you want to follow this story to its conclusion, hit subscribe and enable notifications, because when government reopens and NASA releases this data, we're going to analyze actual findings together. This community will be part of understanding what scientists discover. I want you there for that conversation. Now, let me bring this all together and tell you what happens next. Closing. So where does all of this leave us right now, in this moment, as government shutdown continues and data remains locked in NASA servers, waiting for administrative machinery to restart? Let me bring this full circle. We started with a Congressional letter on October 31, 2025, a formal inquiry from Congresswoman Anna Paulina Luna demanding NASA acknowledge and commit to releasing 3I Atlas observational data, particularly Mars-based observations. NASA responded with specific commitment. Data will be released as soon as government reopens. Then government shut down November 1st and 2nd, creating the delay we're currently experiencing. Luna had a follow-up interaction with NASA on November 6th confirming commitment stands, and now we wait. We wait for congressional action to end shutdown. We wait for administrative functions to restart. We wait for NASA to fulfill its promise and publish the complete dataset, including HiRISE observations and Mars reconnaissance orbiter findings. That's where we are. That's the honest current status. What have we learned through this analysis? First, institutional transparency can work when congressional oversight enforces accountability. Luna's letter created formal record. NASA's commitment created measurable timeline. The principle that publicly funded research should be publicly accessible got reinforced through institutional process. That matters beyond this specific case. It sets precedent affecting future decisions about data release timing and transparency. Second, delays don't automatically indicate conspiracy. Technical processing, institutional verification protocols, and government shutdown are legitimate explanations for gaps between observation and release. Mundane bureaucratic reality explains most of what appears suspicious when you don't understand how institutions actually function. Third, scientific process requires complete data before reaching conclusions. Speculation based on partial information often leads to incorrect interpretations. Waiting for comprehensive datasets before drawing conclusions is frustrating but necessary for accuracy. Fourth, distributed scientific examination is how knowledge advances. When data releases, hundreds of qualified researchers will examine it independently, proposing explanations, testing hypotheses, building consensus through evidence. That process produces more reliable conclusions than any single institution's analysis. What happens next depends on political resolution of government shutdown, which is unpredictable. But once government reopens, expect data release within days to weeks. Scientific analysis begins immediately. Preliminary findings emerge within weeks. Peer-reviewed papers appear within months. Scientific consensus solidifies within a year. Whatever the data shows, conventional confirmation, interesting refinements, or genuinely challenging findings, our understanding expands. We learn more about interstellar objects, about how comets form in different stellar environments, about the diversity of planetary system formation across the galaxy. That knowledge has value regardless of whether findings are sensational or routine. Meanwhile, 3I Atlas continues its journey outbound through the solar system. Between late November and late December 2025, it will move beyond easy observability as distance increases. This creates urgency. Data release needs to happen before scientific opportunity closes. NASA knows this. Luna knows this. Everyone involved understands timing matters. That creates pressure for rapid action once government reopens. What do I want you to take away from this entire analysis? First, maintain intellectual honesty. Distinguish clearly between confirmed facts, plausible hypotheses, and speculation. Don't blur those categories. Second, trust process while demanding accountability. Institutions should follow proper procedures, but congressional oversight ensures they don't use procedures as excuses for indefinite delay. Luna's letter exemplifies oversight functioning correctly. Third, stay engaged with actual findings. When data releases, pay attention to what scientists actually discover rather than sensational headlines or speculative interpretation. Read scientific papers if you're capable. Follow credible science communicators who explain findings accurately. Build your understanding on evidence. Fourth, recognize that advancing knowledge is inherently valuable even when discoveries aren't revolutionary. Learning more about the universe matters regardless of whether any specific observation confirms or challenges existing models. If you've stayed with me through this entire analysis, you're exactly the kind of person this community needs. Someone willing to examine evidence carefully, distinguish fact from speculation, understand institutional process, and stay intellectually honest while remaining open to whatever data actually shows. That's rare. That's valuable. I want you here when data releases. I want your voice in the discussion about what findings mean. So do 3 things right now. First, hit that like button so this analysis reaches more people who care about scientific transparency and evidence-based understanding. Second, subscribe and enable notifications so you're here when government reopens and NASA releases this data. We'll analyze findings together, examine what scientists discover, and build understanding based on actual evidence rather than speculation. Third, drop a comment telling me what question you most want answered when this data finally becomes public. What aspect of 3i Atlas are you most curious about? What would you find most scientifically interesting? Your questions shape future content and show what this community cares about understanding. The story of 3i Atlas isn't finished. It's paused, waiting for government to reopen, an institutional process to complete. But when it resumes, when data flows and analysis begins, you'll be part of understanding what we discover. Stay skeptical, stay curious, stay intellectually honest, and I'll see you when this data drops. Until then, keep questioning, keep learning, and keep demanding that publicly funded science remains publicly accessible. That's how we move forward together.